All right. So today we are finishing our three-lecture uh, arc, discussing things that are roughly, you can call them observers, you can call them controllers with a state, dynamic controllers, depends on what you prefer. And today we're finishing with a very important topic, Kalman filter. If you have a little bit of experience talking to people who do research, or if you read, some popular descriptions of how various even hobby things are done in robotics, you probably noticed that Kalman filter is extremely popular, used very often, especially quadrotors. This type of drones very often use Kalman filters. Every time you have a sensor which is far from being perfect, it seems people use Kalman filter. In general, it is one of those things which you sort of hope to be able to do, right? So today we will learn why. Why do you need Kalman filter? And today we will try to understand like the mathematics behind it. The material is going to be a little bit difficult as usual, I guess. So if you have any questions, just interrupt me at any time we'll discuss. All right. And last thing I want to say before we begin, with Kalman filter, the situation is quite similar to a lot of other topics such as LQR, PID. Namely, you can quite easily dispense with mathematical background and simply treat it as a recipe, right? So with LQR, just to remind you how you can treat it as a recipe, you can write something like this in MATLAB, right? And this would give you LQR gains. You don't actually need to know much about how Hamilton-Jacobi-Bellman guarantees optimality. You don't need to know Riccati equation. Everything here is okay. In Python, you are forced to do two-step process, right? You find P, and from this you find K by this three matrix multiplication. Still kind of similar stuff. So you can treat it as a recipe. And Kalman filter, I think, very commonly is being treated as a recipe. The only problem is that as soon as you go beyond the simplest form of discussion of Kalman filter, you no longer can kind of ignore the mathematics behind it. So our desire to understand math for Kalman filter is based on the fact that it is actually going to be useful when we are going to go beyond application in the simplest case, which is quite common right now. And also a recipe, it's no problem, right? You find it on Wikipedia, how to generate Kalman filter gains. Like you can do it 5 minutes. But explanation of what is going on, that is harder to find. So today I hope to provide you explanation, right? Whereas the recipe is still quite simple. You can always look it up. So that's, you would see the recipe in the end of the lecture, of course. It is just that I think understanding mathematics here is important in its own right and harder to find. So that's why we concentrate on that. All right, so let's begin. Let's begin. So before we can discuss Kalman filter, we need to discuss random variables. Kalman filter is a object that deals with random disturbances, right? We'll see it in a few slides, so I'm not going to dwell too long on that. But it deals with random disturbances. So we need to understand what those are, and for that we need mathematics of random variables. So let's spend some time understanding that mathematics. So let's say we have a random variable v. we can think of it as a sequence of values, v1, v2, v3, sampled from a distribution. All right. I'm not sure how long I need to spend on discussing this point, but you can imagine you have a distribution which basically gives you probabilities, if you want, chances of getting any particular value of your variable. All right. So, for example, for the most famous, maybe already a little bit you are tired from it, example of the dice, you have a completely flat probability of getting any of those, 1, 2, 3, 4, 5, 6, right? The probability distribution is completely flat. So sampling from this distribution gives you equal probability of getting any one of those 6 discrete numbers. As you can imagine, probabilities do not have to be flat. Like a Gaussian curve goes like this. Very typical probability distribution. Also, as you can imagine, doesn't have to be scalar. You can sample each component of a vector from a distribution. Like each component can have its own distribution. And then you have a random variable like as a vector. And of course, also, it doesn't have to be independent. Components of a vector don't have to be independent. You can imagine like a Rn plane with a vertical axis going as a probability, and you sample from it like the probability of getting any vector on this Rn is given by this vertical axis. Right? So it doesn't have to be independentized. All right. Now, a mean of a variable, of a random variable, we would denote it with a bar. I will put a bar on top of a variable to indicate that it is a mean. We denote it as E square brackets of the variable name, right? So E square brackets, that's going to define a mean, right? Mean operation. What is a mean? I don't like, bringing those how should I put it, like linguistical tricks because they're dangerous. But very roughly speaking, you can think of it as average, right? Of course, you need to be careful because in statistics, every word is defined. What is mean is defined. What is average is defined, and so on. But if you had a very big sample of your variable, you can add up all its numbers, divide them by the number of samples, and you get a value. This value, as number of samples approach infinity, approaches this mean value. All right. So, yeah. Okay. So this mean has a number of properties. Some of those properties are quite interesting. Like, for example, mean of a constant is a constant. Why? Well, because no matter how many times you sample this constant, you get the same value, right? Then you'll find average of those same values. You find, again, value A, right? You get A. You sum them, divide by the number of samples, you still get A. All right. Another property, mean of a sum is sum of means, right? This you can prove by considering definition of a mean, right? Like a sum over blah, blah, like divided by n. When you open it up, you can separate the terms, put brackets, and you'll get this situation here. So those should be quite obvious. This should be quite obvious. Mean of a random variable times a scalar is the same as a scalar times the mean of a random variable. So the scalar can get out of the mean, right? And same with the matrix. Mean of a matrix times random variable is the same as matrix taken outside the brackets times mean. If you want to prove all of those properties, simply write out definition of a mean and perform those operations. So it will be limited to taking out of the brackets whatever you want to take out of the brackets. That's easy to prove. So if you feel unsure with that, good exercise to prove all of those. For those of you who remember linear algebra pretty well, you may recognize this as some linearity properties. Like it feels like this mean function is linear, right? So is a good indication, is a good sign. We like linear functions. Okay, all right. So those are random variables and mean. Now, next thing we need is autocovariance. There is a covariance that's separate entity, but we're not going to use it. We're not going to use it. So instead, we're going to use only autocovariance. All right, so that's why I'm defining only this one. So autocovariance V, capital V, is defined as covariance of V with V, right? And more concretely, it looks like this. It is a mean of a outer product of those two vectors. So let me be careful now. Vector number one, vector number two, transposed. Okay. So outer product is vector transpose. That multiplication is outer product. You're familiar with inner product, which is given as x transpose x, right? Oh, x transpose x is a dot product, right? Basically, what it produces is sum of components of x squared, right? That is essentially what inner product does. Outer product, you can just follow the definition. It is a vertical vector times a horizontal vector. So if x was in Rn, the outer product will give you a matrix in Rn by R in n by n matrix. All right. So for example, for 3 by 3 x, it would look something like this: x1 squared, x1, x2. Let me get more space between those. x1, x3, right? That is the first row. x2, x1, x2 squared, x2, x3, and finally x3, x3, x1, x3, x2, x3 squared. So that would be how outer product would look like for a vector with 3 components. So you can imagine each component of the first vector multiplies every component of the second vector. All right. And this generates the first column. And I'm talking about, let me be careful again. Each component of this vector multiplies the whole horizontal vector, multiplies the whole vertical vector. That gives you the first column. Then the second component of this horizontal vector multiplies the whole second vector, gives you second column. Then the last one multiplies the whole vertical vector and gives you a last column. All right. Those two operations are like inner product, outer product, perfectly legitimate operations, normal, used very often. Okay. So here what we have is outer product between those two vectors, right? Outer product between those two vectors. So we know that the result is going to be a matrix. Now, what are those vectors? Let's see carefully. It is the difference between V and mean of V, all right? So you can imagine a variable, random variable, minus its mean. So you can think of it as a distance from the mean of a current value of a variable. Let's say your variable is something like 1001, 1002, 1005, 995, 996, 993, and the mean, let's say, is 1000. Or you subtract it, and what you get is something like -5, -3, 2, 5, 1, -2, etc. Right? So the distance from the mean. As you can imagine, this is quite convenient, like this, thinking about it this way, distance from the mean, right? But yeah, regardless of that, that is simply definition. You get your variable, subtract from it its mean, and what you get is this distance from the mean, right? Then you find outer product of this vector with itself, and you find its mean, all right? You find its mean. Of course, as you can imagine, like this part, the mean of a mean is just a mean, right? Mean of a constant is a constant itself. So this operation mostly is needed for this guy. Okay, okay. So far it looks a little bit, maybe a little bit scary, but it's not very scary. Now, just to make notation a little bit simpler, we would sometimes write it like this: covariance of V, which would imply outer covariance, and it would imply a covariance of V with V, right? Okay, now let's say you have a zero mean process. Process is another way to say a random variable, like both of those are similar, you can say. Definitions of this similar. So let's say you have zero mean process. So the mean of variable V is 0. Then in the formula above, you have simplifications, like this goes away, this goes away. And what you have is covariance, outer covariance of V is just a mean of outer product of V with itself. All right. So if mean has zero mean, if V has zero mean, then you simply find outer product with itself and find mean over it. That's all. That's all. Okay. All right. So autocovariance has properties. One property is autocovariance of a constant vector is 0. Why? Well, when you take a constant vector and you subtract its mean, it's going to be 0, because mean of a constant is a constant itself. So you would have 0 there. 0 times 0 is 0. Covariance of x plus a constant is covariance of x, because adding a constant will only shift the mean. Right? When you do this operation, the constant will be deleted from the expression. So is a covariance of x plus a constant is covariance of x. Autocovariance. Covariance of lambda times x is lambda squared times covariance of x. Why is that so? Well, because we have, you can imagine, it is a, how should I put it? It is a quadratic formula. So lambda would be in front of the one vector and in front of another vector. So you'd have two lambdas. You can take them out of the brackets. using the properties of mean, right? You can always take them out of the brackets, and but you will have two lambdas, two alphas, because you have two variables multiplying each other, each multiplied by lambda, so alpha. My apologies. So you will have two of them, so that's why you have alpha squared. Okay. All right. Now, there is a very interesting property that a random variable x with Gaussian distribution can be fully described by its mean and its covariance. And we can even write it like this. Say x is sampled, this is how you read this symbol, sampled, from a Gaussian distribution, normal distribution if you want, Gaussian distribution, with a mean x bar and covariance capital X. All right. For other distributions, this might not be true, but for Gaussian distribution, it is. So this allows us to be able to discuss all of those things simply in terms of their mean and their covariance. Very useful, of course, very useful. So instead of thinking about something quite complicated, we think about simply two numbers which come from linear operations, essentially. You can think quadratic operation for covariance and linear operation for mean. So very good property, very good property. Okay, I think we're done with, no, we're not yet. But okay, before I continue, any questions about any of this? Okay. Now, we can discuss a mean of a linear transformation. That is going to be extremely useful for us, so we need to spend time on it. So mean of a linear transformation. Let X be sampled from, like in this case, Gaussian distribution. All right. And we have our constant matrix M. When I say constant here, I simply imply that it is not a random variable. Okay. So we can define a affine transformation of X as Y equals to M times X. But X, remember, is a random variable, right? So let us find mean of Y. Well, we already did it on the first slide, so it's not like we're doing anything new. But let's just do the exercise. It's going to be useful. So mean of Y is equal to mean of M times X, okay? Which we can put the M out of the brackets, as we said previously, right? So mean of Y is equal to mean of X times M, right? And we have a relation between what here we can write it as Y bar is equal to M times X bar. So essentially what we discovered is that linear transformation acting on a random variable is kind of the same as, it has the same structure as a linear transformation of its mean. So the mean of a variable is being transformed in the same way. This is not something you need to memorize. It's not something that you need to somehow, internalize or whatever. It is. I'm just showing you how you do this exercise. In this case, it is kind of trivial. Right? Okay. And if X bar is 0, then Y bar is also 0. Right? So linear transformation of a zero mean variable results in a 0 mean variable. Okay, so mean is not going to be shifted by linear transformation. Okay, so far I think kind of easy, what about autocovariance? That sounds a little bit more challenging, right? A little bit more challenging. So let x bar be equal to 0. Okay, so we have 0 mean. Just for simplicity, we don't have to make this assumption, but it is going to make mathematics much easier. And as we will see later, it is a very typical assumption that we make in the Kalman filtering. So this assumption saves us a lot of trouble. But it is not like mathematics is impossible to do without this assumption. So if you don't like it, you can do everything without it. It's just going to be bigger. That is all. Okay, so assuming that x bar is equal to 0, then we know that y bar is also equal to 0. So mean of x, mean of y, both 0. Let us find autocovariance of y. Autocovariance of y is equal to mean of y minus mean of y times itself as an autoproduct. Okay. But since we said that mean of y is equal to 0, this goes away, right? So we have mean of y transpose, autoproduct. But y is equal to mx, so it is mx times mx transposed. We can open the brackets, and what we will see is mx times x transpose, m transpose, right? Let me, I guess, quickly use color coding. So mx, right, times x transpose, m transpose. That's what we have. That's what we have when we open the second bracket. But of course, this central expression here, x transpose, the mean of this expression is just covariance of x, right? Autocovariance of x. And those m matrices can be thrown out of the brackets. Like we can throw them out of the mean. So we basically throw m in, like in front of mean here, m transpose out of like I don't know, like this m behind the mean, this m in front of mean, and then we have m, x, m transpose. Okay.
Oh, excuse me.
Yes.
Can you hear me?
Yes, I can hear you.
May I have a question?
Yes.
So, why do we need this? Why do we need autocovariance? What does it represent?
What is autocovariance?
Yes, and why do we need it?
So why we need it? We will see when we start, like why we need it, right? We'll see when we start Kalman filter. Because with Kalman filter, autocovariance is the key of the Kalman filter. I'm a little bit hesitant of trying to sell you the idea of autocovariance as a useful statistical property. Other than, I can remind you that autocovariance, together with mean, completely describes a random process, with a Gaussian random process, okay? So if you're willing to work with a random process, Gaussian random processes, basically all you need to know about them is the autocovariance in their mean. You cannot do without autocovariance. You have to have it. Same as the mean, you have to have it. So if you're going to work with random processes, you have to have it, right? It describes your process. Yeah. What it represents, I'm not sure if I have like a very good visual expression of what autocovariance means. Like we could try to find the verbal construction about that, but I don't think it will actually help much. So I would recommend, it's my personal recommendation, okay? I'm sure there are plenty of like YouTube videos or textbooks which would explain to you autocovariance in nice human terms. But my recommendation would be to just accept that, oops, sorry, accept that it is this guy, right? Autocovariance. It is just this guy. This is how it is defined. And we need it for practical tasks, right? That is just my recommendation to how to think about just a mathematical object, right? Same as like yeah, I don't know, but I'm sure some people would be able to give you very more visceral description of what autocovariance means in the real world. But for us, again, the idea is that we'll be able to describe a random process with autocovariance, and later we'll be able to use it to design Kalman filter. That's the idea.
Okay, thank you.
No problem, no problem. All right. So one more time, autocovariance of y, where y is equal to ax, is given as m times x times m transposed, where x is autocovariance of x. So what we saw is a linear transformation of x, which is given as ax, y is equal to ax, translates to transformation of covariance of y as m x m transposed, right? So this first expression is how the variable is transformed. It is how the mean is transformed. Both of those are equivalent. The second expression is how the covariance is transformed. Okay, all right. Now we have enough mathematics. We can start with state estimation. We can start with state estimation. So let us try to do it. Let's try to do it. So we'll consider discrete time linear time invariant systems, right? Where we have x sub I plus 1 is equal to a times x sub I plus b times u sub I plus w sub I. Now, our w will be a random process, okay? A random process, a random variable. It will be sampled from a Gaussian distribution with a mean of 0 and with a covariance of q. And this is going to be called a process noise. Covariance is positive definite, right? Positive semi-definite in this case, right? So before we move on from this point, let us try to understand it a little bit. So what does this mean? What does this mean? First of all, why does it need to have 0 mean? Oh, it doesn't have to, but if we have a not 0 mean process, we could always subtract the mean from the random variable w and add it to here as a constant variable, like let's say plus c. Okay. So if c is the mean of w, we can subtract it from w and get a 0 mean process. But c would be just a added variable. This is possible, but for us, like all of those, each time you see something like this, where you have a linear system, but somehow you have a constant term added, you need to remember that, first of all, it is not so difficult to deal with this. So there is nothing too difficult about it. Second, we just deviate from linear systems to affine systems, right? That's a more general class of systems where you have added constants to the right-hand side. Is it going to be completely different mathematics for Kalman filter or for LQR or anything like that? Oh, it's going to be different, but it's not going to be completely different. which is why we don't spend time discussing it in the course. Like you can rederive LQR for the system with this type of right-hand side. Is possible. You can derive a control that would deal specifically with the system with this added C, and so on and so forth. Is always possible to deal with it. It is not a catastrophe or a limitation. In fact, most systems would have this kind of addition, this C. Okay. So is possible to deal with it. But we don't spend time on this because like we want to stay, how should I put it? We want to avoid going into deep waters where we have like more mathematics and less concepts. And essentially adding C here would just increase mathematics without giving you more concepts. So just remember, if you have something like this, it's possible to deal with it. You can try to derive it yourself or you can look it up. But yeah, for our course, we are not very interested in this, in those additions, which by itself justifies already zero mean of the process noise, right? It is if it wasn't zero mean, we would just have this additional constant, and that's it. Right? Okay, okay. So the process noise is completely defined by its covariance, autocovariance Q. Okay, completely defined by its autocovariance Q. Okay, so how do we deal with the system? Notice we have a system where next state depends on the previous state in control. And on top of that, it depends on a random variable. So previously we were able to at least expect what's going to happen next based on what happened previously. Now we cannot because there's a random variable. It can do whatever. So it feels as if the task of controlling the system becomes much, much harder. In fact, since there's a random variable, how can we even discuss stability of the system, right? How can we discuss if the system is stable? If on any point of time, it can jiggle somewhere very far away from the origin. As you remember, Gaussian distribution is kind of like this. It has a very long tails. The chances of getting anywhere on the tail is very small, but not zero. So you can always jiggle all the way out. So it feels as if this this system will be difficult to control. Okay, and x, it means x itself is random, right? Even if the initial x was certain, next x is already a random variable because it is a certain variable plus a random variable gives you a random variable. Okay, so it sounds very hard. Okay, why would we even consider those systems? Well, problem is almost all systems behave like this. This is not a bug. It's unfortunately just a fact of life. For example, if you have a airplane, it flies through air. Air acts as a random noise, right? It influences your dynamics, and it influences it randomly. You cannot model the air. You just have to accept that there is a random disturbance. That's what we call a process noise. Same is true for autonomous car. Same is true for underwater robot. To an extent, same is true even for industrial robot, as long as it encounters any unexpected events, such as, for example, when doing pick and place, it can encounter like friction where it didn't expect friction. It can encounter slightly different weight, and so on and so forth. Even or yeah, just the friction in the joints can be random. For industrial robots, you can just avoid it. You can model everything correctly, and you can try to minimize randomness in the environment, and then you don't have to think about it. But it's just normal for the world to have some degree of randomness. So you shouldn't expect to be able to get away with it without it, right? Especially for autonomous vehicles. Autonomous vehicles of all types, drones, cars, underwater, etc., all experience randomness that comes from the environment. If you're going to work with cobots, like collaborational robots, they would experience this. If you're going to work with the cleaning robots, they're going to experience this. So randomness is normal. We have to be able to deal with it. So far, all our instruments, like LQR, PID, pole placement, they don't answer this need. They don't tell us anything about how to deal with this. So we need to design a way to deal with those things. All right. So for now, let us just propose how we're going to observe this, right? Let's say we don't have a full state information. Let's say we don't have a full state information. So we need to design an observer for the system. Okay. That is a little bit of a tall order, right? But of course, if we know the full state of the system, the situation is much simpler, right? At least even if X is random, at least we know what X is, which is, by the way, one of the reasons why industrial robots don't have as much problems, because you usually measure the entire state directly. Yeah. So anyway, let's design an observer. So we will do it, start the same way as we did with Lundberg. So we have next state of the next observed state, next state estimate to be equal to previous state estimate plus B times UI. So basically just takes a certain part of the dynamics and reproduce it here, but for the observer. I remember we previously talked about it as a open loop observer. We know that it's not going to work, but it is the first step. We will improve it in a bit. But we start with the same, right? Just the estimation is going to change in the same way as X changes, but without a random variable. Because the random variable, we don't know what it is. We cannot add it to the observer, right? It is random. We don't know it. Okay, all right. Now we can find estimation error. The error will be denoted as X tilde. It is defined as X minus X hat. So X minus X estimate. So X tilde would be given as a difference between this guy and this guy. So it is going to be AX minus AX hat. So giving us AX tilde, right? BU minus BU, giving us 0. And omega minus 0. So gives us omega. So we can see that estimation error, in this case, would act this way. Next estimation error would be equal to previous estimation error multiplied by A plus a random variable. Okay, so far, I think understandable, right? Now, the trick we're going to do is we're going to compute means and covariances for every single expression that we have here. So we're going to do it again and again and again, so don't be surprised. We're going to continue doing it. It is doing this will allow us to derive Kalman filter. So let's start with a simple case. So assume you can pick your initial state, x0 hat. That's initial estimate, initial state estimate. Okay. And we pick it in such a way that the initial state estimation error, x0 tilde, behaves as a random variable sampled from a Gaussian distribution with 0 mean. That sounds like a tall order, but let us understand what we are actually asking. So what we are asking is that the way you pick your initial state estimate does not have a bias. So we want to avoid you picking something with a clear bias, where the error, state estimation error, your initial pick, would always have a bias in a certain direction. That is what mean is, essentially, is a bias in this case. So we want to avoid it. We don't want your state estimation to be biased towards certain direction. And we want it to be Gaussian. Okay, that sounds maybe a little bit harsh, like how do you do it? But suffice it to say, usually you almost always are able to pick your initial state estimate with a zero error. Because often you start from a position which is already known. So if for a car, for a drone, or for underwater robots, for all of those, often you already know your initial position. So it's not a big deal to pick a zero error initial state estimate, right? But if you think this is a big assumption, good, keep it in mind, because it is an assumption. And how you're going to, in practice, make sure that you have a Gaussian distribution? Good question. You can ask yourself that, right? But we'll make this assumption. We need it. So, okay. So our initial error will be sampled from a Gaussian distribution with zero mean and covariance P0. Now, let us see how the dynamics of the estimation error works. So if we know E sub x tilde I, we can compute mean of x tilde I plus 1. How do we compute it? Now, mean of x tilde I plus 1 is equal to mean of A x sub I plus omega I, right? But mean of omega I, wi, is 0. So let me just point it out. Mean of this guy is 0. So essentially what we have is mean of x sub I plus 1 is equal to A times mean of x sub I. But if the initial mean is 0, it means all subsequent means would be also 0. Because all we do is we multiply it by A each time. But 0 times A is 0, no matter how many times you compute it. So the mean of the entire thing is going to be 0. So, okay, let me summarize what we achieved right now. We found that if the initial mean of state estimation error is 0, all subsequent means of state estimation error would also be 0. So in terms of mean, state estimation error does not have a dynamic other than 0, 0, 0, 0. So it just stays 0 mean to all eternity. The reason we were able to do it is because we made two assumptions. One is this assumption. Another one is assumption on the mean of omega I. Okay. If it wasn't for that, we wouldn't be able to do it. But okay, all right. That is a good start. That's a good start. We already know something about our estimation error. Now let's move on. And let's compute autocovariance P sub I. Knowing P sub I, we will compute autocovariance P sub I plus 1. This might look a little bit technical, but let's just persevere through it. It's not very difficult. So P sub I plus 1, so autocovariance at the moment of time I plus 1 is equal to x tilde I plus 1 times x tilde I plus 1 transposed, which is the same as a x tilde I plus omega I times a x tilde I plus omega I transposed. Okay. Please notice that we already use the formula without mean because we know that the mean is 0. Okay. All right. Now, when we open these brackets, what we are going to have is this will multiply this, right? So we are going to have A times x tilde transpose A. We're going to have two terms which would look like this. AX omega and omega x A, right? That comes from multiplying those together. And we have omega times omega, right? So we just open the brackets, we get AX A, right, from here. Then AX omega transposed, that is multiplying this by this. Omega times X times A, that's multiplying this by this. And omega, that's multiplying this by this. Now comes the first non-trivial part, which is easy to, it's easy, but you need to hear it. You need to hear it. So we can assume that the random process W is uncorrelated with X tilde, meaning that the mean of Xi omega I transpose is 0, and the mean of omega I X tilde I transpose is 0. We didn't look into correlation, like we looked at the covariance, we don't autocovariance, we did not look into covariance. But the covariance has a property. If two processes are not correlated, then the mean of their, basically then the covariance is 0, right? And we can easily assume that our process noise does not depend on our state estimation error, like they completely separate. Okay, so this is an assumption. This is an assumption. All right, all right. At this point, there might be needed some how should I put it? Might be needed some comments, I think. But it is a little bit technical, so I'm hesitant. But okay, I would say it. But if it is not clear, okay, you don't have to. Like it's okay. It's not critical. But okay, when you look at the expressions here, it is very tempting to think that the random process in question is a process that takes us from x1 to x2 to x3 to x4 to x5, right? X tilde 1, x tilde 2, x tilde 3, x tilde 4. But this is a random process, right? Random variable. Like new samples of this random variable come from marching forward, right? That's very tempting to see. That's incorrect. That is incorrect. Same with omega. It is very tempting to think that random process here is omega 0, omega 1, omega 2, omega 3, omega 4, right? That this is how the process marches forward, and this is the random variable. That is technically again incorrect. Technical. Okay. What actually is going on here? What actually going on here is this. X sub I, specifically X sub I tilde, is itself a random variable. So assume you have to perform 1,000 experiments. You have the same robot, let's say autonomous car, and you drive it 1,000 times. And you have your initial state estimation error sampled from a random Gaussian distribution, right? Gaussian distribution with P0 as its covariance and 0 mean, okay? What you will see is that in those 1,000 experiments, X sub I tilde will be a random variable. Like you'll have 1,000 samples, of x sub I tilde. That is the random process in question. You would have 1,000 samples of x sub 0 tilde, so initial state estimation error. That is a random process. You will have 1,000 samples of omega 1 or omega I or omega 10 W, okay? All of those. So the question is not that there is a random process that happens in one experiment. That's not it. The question is, you have 1,000 experiments, and across 1,000 experiments, you have 1,000 samples of a single entity. For example, x tilde 10. So 10th step, x tilde. You have 1,000 samples of that. That is a random process. That would have covariance P10. That would have 0 mean. Okay? So it is not correct to think about it as I will compute covariance by adding x1 times x1 transpose plus x2 times x2 transpose plus x3. That's not it. That's not it. That's not correct. You perform many experiments, and across those experiments, you find covariances. So that is why it sounds like this statement here is completely bonkers, right? You would say, okay, how is it possible that x tilde I, which clearly is begotten by, multiplying previous x tilde times a plus omega I, right? How is it possible that it is independent from omega, from W? But it is independent because we're not talking about the progress in time forward. We're talking about across multiple experiments. Across multiple experiments, those two are independent. Okay, so that is the idea. If that was not clear, that's okay. It is not it's good to understand this, but we'll be able to move forward without. Okay, but it is good to understand. Okay. Now, what we achieved is this. We know that since this is 0, this goes to 0. Since this is 0, this goes to 0. Therefore, this guy and this guy are the only ones that remain. Okay. But we can easily deal with those because let us remember, 1 second. This is just P sub I, right? Covariance on the previous step. And this is just Q, right? It is a covariance of the distribution from which it's sampled. It is sampled. So what we find is covariance on the next step is equal to covariance on the previous step, conjugated by A transposed plus Q. So that is how covariance of the estimation error works. As you can imagine, it's going to increase, right? Likely, unless A quickly diminishes P, right? Unless A shrinks P down, it's going to increase because there is this added term Q. Each time it is positive definite. P0 is positive definite. So if A, for example, is identity matrix, it's going to increase. Okay. All right. Any questions so far? All right. Now we found mean and we found covariance. Means stays 0. Covariance changes as P sub I plus 1 is equal to APA plus Q. Nice. We know what's going on now. Now, as previously, as when we discussed Limburger, we know that open loop observer is not going to do much for us, right? We want to use measurements. We want to use measurements. So to do that, let us first introduce measurement model. So we say it is yi equal to hxi. Notice usually we have c here, but for Kalman filter, it is common to use h. So we'll just use h. Plus vi, where vi is a random process called measurement noise, which is again sampled from Gaussian distribution with zero mean and covariance R positive definite. Okay. All right. So what is going on here? Why do we have one more random process? Well, this I think is even more concrete. So imagine you have a sensor, right? You have a sensor. Does the sensor produce exact correct information? Probably not. It probably has some error. Well, if we're lucky, the error would be Gaussian distribution zero mean. If the error is not zero mean, basically means we have a biased sensor. And bias in the sensor is usually easy to correct. If you know that, let me dwell on this point for a second. So let's say you know that your measurements are not zero mean. So you have a process measurement noise, and your mean is, let's say, five something, like 5 degrees. Okay. So you always measure with average error of 5. Okay, the actual errors all over the place, but 5 is your mean error. Well, what you do is just you add subtract 5, right? You say, okay, we will in our computer take y and subtract from it 5. How do we know that it is 5? Well, we can test. Sensors are being produced at a factory where they will be tested extensively. So whereas environment, you can argue it is hard to test it exactly, but sensors, clearly you can test it exactly. You can produce experiments which would allow you to find out your covariance of your noise, if it is Gaussian noise, and mean of your noise. And if you have knowledge about your mean, you simply subtract it from the sensor, from the readings of the sensor, and you get zero mean measurements. So that is why it makes perfect sense to have a zero mean Gaussian distribution as your measurement noise. Okay, okay.
Oh, excuse me.
Yes.
So this not this random variable with noise is known for us, whereas W, which is also noise, process noise, we do not know.
We don't
Am I
know.
correct?
We don't know either of them. It is just that both of them have zero mean, and both of them have known covariances. So we assume that we know covariances for both of them. So in this sense, they're exactly the same in terms of our knowledge. It is just that here I can argue very convincingly why this model works. Why zero mean makes perfect sense is because sensor is just easy to correct for biases. So easy to correct for non-zero mean. We just subtract something from y. But mathematically, situation is exactly the same between v and w. They exactly the same situation mathematically. Practically, measurement noise, I can easily argue that zero mean is correct. Whereas for process noise, my argument was not as strong. But that is, mathematics here, practical life here. Important not to mix the two. Mathematically, those two are exact same object. Different autocovariances, but otherwise the same exact like style of object. Yeah. So,
Okay, thank you.
no, thank you for the question. Okay. Oops. So we have our measurements. So even our measurements are not exact, So like previously we could at least hope that we would know something about the x and we'll be able to control it. Now even our measurements are random, so we don't know what to expect. We don't know if this is going to be good or not. So big problem, big problem. Now let's see if we could actually solve this situation. Well, here more technical stuff. So let us just survive through it. It's not very difficult, but yeah, a lot of mathematics. So let us propose the following modification of our observer. This is what we proposed previously, but now we have additional subscript minus here. Minus is being read as a priori. A priori means prior to, previous to. Okay. So basically, what this guy means is that is our observer before measurements. Okay. Well, this is our estimation before measurements. Okay. Now we have a separate one, second equation, where we have our estimation after measurements. Sometimes we call it a posteriori, but you just call it x hat. Okay. That is given as a priori measurement. So a priori measurement, let me color code it. A priori measurement. Plus the same exact thing as Leuenberger. So control gain times the difference between measured output and expected measured output. So expected measured output is y equals to hx a priori. In this case, a priori here. Why is it so? Well, you remember in Leuenberger, what we wanted essentially is to find delta y, like how far we are from our correct measurements. We couldn't compare x directly because we don't know x, right? But we can compare y directly. But here we have a little bit of a problem that y contains measurement noise, but we don't know what measurement noise is on this time step. Like we cannot find it. So we have to compare it with h times x by a priori. That is the best we can do. That's the best we can do. Okay. Now, this last expression, we can rewrite, and let me color code it again. We can rewrite saying that this a priori measurement plus again our L sub I plus 1. And now instead, let me use a different color code. 1 second. Instead of y, we put it as x sub I plus v. And of course, minus h a priori. So essentially, the last equation would look like this, right? It is our state estimation will depend on on the second step, on the would depend on our a priori estimation, which we discussed previously, plus lambda, our gain, times this expression in the brackets. All right, that is a proposition. That's the proposition. So we can do the same as before, but with just minor differences in terms of notation. So we can define our a priori error, which is x sub I minus a priori estimate. And with that, what we can do is the following. Like, first of all, the first equation then would become like this if we subtracted dynamics from it, right? So it's exactly the same as before. We'll get to it, but yeah, this is why we defined this guy. Okay. Okay. So this equation, what we will do is we subtract dynamics. We subtract x sub I plus 1, just x sub I plus 1, from both sides. So what we get is, on the right-hand side, here, we have xi minus xi plus 1. On the left-hand side, we have a priori minus xi plus 1. The rest is the same as before. Now we can flip the sign. We can flip the sign. And having this definition, we get our final expressions. So this comes from, like we did it before, right? We subtracted from it from the dynamics, and we got this expression. So nothing changed. It's just a notation now includes this a priori minus sign. This guy, what happens? Well, basically, it is like this guy here. Let me be careful. Did I make a mistake here? I make a mistake here. Let me be careful. Yeah, I think I made a mistake here. This should be I plus 1. This should be I plus 1, and this should be I plus 1. Okay. So when we do this, like our color code, this guy becomes this, right? Simply from our definition. We flipped the sign, remember? So that's why we don't have a minus sign. Now, this guy is I times this. And this times LH becomes this times LH. And finally, V times L is this guy. Right, I apologize if there's a lot of like linear algebra shuffling. Yeah, but I think it's quite clear. So what we did one more time, we introduced this new variable, subtracted from like this. So this equation automatically becomes this equation, as we said previously, by subtracting dynamics. And the last equation we get by subtracting x plus sub I plus 1 from this guy, flipping the sign, and collecting the terms. Like this term gives us I, this term gives us LH in front of the same variable. There is a error in terms of subscript. Okay, all right. So this is how we get our error dynamics for our observer. Looks kind of interesting. So as you remember, what we are playing right now is finding means and finding covariances. So that's what we're going to do very soon. So mean, as you can expect, is going to be 0. But let's just quickly look at it. So mean of a priori is, as we said previously, right, is mean of a x tilde I plus omega I. Omega I has 0 mean, so it is a x tilde I. All right, this is 0. So it is a x tilde I. Okay. And mean of this guy, we cannot conclude, by the way, now that it is 0, because we have two rows. We need to both of them to be linear. So we can conclude 0. Okay, this a posteriori estimate now is E times E of x sub I plus 1, where we have this matrix I minus LH times a priori plus LIVI. Well, it is a sum, so we can, like, LIVI clearly has 0 mean because VI has 0 mean. So it will be 0 times L, give us 0. So this goes away. So we have I minus LIH times a priori. So essentially what we have is, again, it is a matrix times the mean on the previous step. So this is our mean dynamics. As we can see, if initial value is 0, then the next value will be 0. Then the next value will be 0, and so on to infinity. So dynamics, mean dynamics, even in this formulation, still 0. So that's how we prove it. That's how we prove it. Okay, right. So mean remains 0. Now, interesting part. Let us compute autocovariance for a priori estimate. Essentially what we already did, right? Here is our a priori estimate, a priori times a priori transpose. So it is this guy, we already did it, right? It is going to be AX X transpose A, where X transpose is going to give us PI. So that is our API A transpose. We're going to have those components which will be 0, right? And we're going to have Q here coming from VI times VI transpose. Okay. So this a repetition of what we did previously. Now, more complicated mathematics, right? But like, you know, not very complicated, not very complicated. So a posteriori covariance looks like this. So a posteriori times a posteriori transpose gives us I minus LH a priori times a priori transpose I minus LH, right? Plus I minus LH a priori times V transpose plus V times a priori transposed times I minus LH transpose plus lambda alpha, L V and C transpose times L transpose. Okay. All right. Good. I think here we're missing also L in both those expressions. Right. How did we get it? We just opened expressions for both of them and you know, just opened the brackets. That's what we did. Now, as before, you can imagine this guy would be uncorrelated, so the covariance would be 0. So essentially, this is 0, this is 0. Because we are multiplying here, finding correlation within two independent processes, X and V and X. Right? They are independent, so we can assume they are uncorrelated. So they are going to go away. So as before, these guys disappear. And what we have is something quite simple. So our covariance is equal to I minus LH P a priori times I minus LH transpose plus LRL. Where does this come from? Well, it is from here. LR, like V times V transpose. The covariance is R times L transpose. And all of this is equal to P sub I plus 1. So notice what we were able to achieve here is we found the covariance on the next step using our a priori covariance. So we found a posteriori covariance knowing our a priori covariance. Okay. Again, let me remind you that covariance completely describes the process. So we know exactly how on the next step, our observer will behave in terms of estimation error. Simply from this equation. Simply from this equation. Okay. Now, all of this was a preliminary to very simple resolution of finding Kalman filter gain. Kalman filter gain. I mean, when I say simple, I'm maybe lying, but we'll see. We'll see. It's not very difficult. So now we know how covariance propagate. Now, the question we will be able to pose now is how to minimize those covariances. Basically, we want to minimize the error of our Kalman filter observation error of our Kalman filter. And we will be able to do it. We will be able to do it. All right. But we need just a couple more preliminaries for that. I apologize for mathematical content today is quite large, but yeah, a little bit more mathematics. So first of all, we need the fact that inner product is equal to the trace of the outer product. Okay. Why is this true? I'll consider x1, x2, x3 vector. So inner product is x1 squared plus x2 squared plus x3 squared. Here's outer product. You can see its trace, x1 squared plus x2 squared plus x3 squared is equal exactly to the inner product. So just a interesting fact. Trace of the outer product is equal to the inner product. Okay, that is one mathematical statement. Another one that is complicated. I'm not going. We're not going to spend time on this, but basically, you can take derivatives with respect to trace. Okay, sorry, of the trace. So if you have a trace of a matrix times like A times X, you can take derivative with respect to X, and it's going to be A. Okay, of the trace. Remember, we are talking derivative of the trace. And there are formulas for all kinds, like trace of A times X transpose with respect to X gives us A transpose, and so on and so forth. Even for this kind of case, where you have X transpose times A times X, you have a derivative with respect to X, which should be equal to X transpose, A plus A transpose. We're not going to look into it too much. I'm just pointing out that this is possible. There are those tables. You can find them online. You can also just verify it for yourself. Simply write it out for a case of like 2 by 2, 3 by 3. Write it all out, see what you find. It's not going to be very difficult to verify those formulas. So I recommend doing it. Okay. All right. Now, I apologize if it was scary, but we're not going to how should I put it? We're going to use it very light, so don't worry. Now we want to find optimal gain for the Kalman filter, such that we can minimize our observer error. Okay, on the ith step. So notice what we have here. We have here a sum of squares for the components of the error. And I want to minimize expectation of this. It would be pointless to try to minimize x sub I itself, because we don't know what it is. It is an uncertain variable. It doesn't make sense to try to minimize the variable itself. What we can minimize is its expectation. So it's mean. That would make sense. Trying to minimize this doesn't make sense, or by itself without mean. Okay. Now, of course, we remember, covariance of on the step I+1 is defined this way, right? So it reminds us a little bit of this guy, right? But not exactly. Like this essentially is inner product, right? This essentially is outer product. Okay, right. But we know that the formula tells us that the trace of the outer product is inner product. So we can minimize the trace of this guy, right? The trace of outer product is inner product. So that's what we want to minimize. All right, that's where we used our first piece of mathematics, the trace formula. Okay. Also, expectation, like mean of trace is the same as trace of mean. They're linear operations. They can, I mean, in this case, they can exchange. It is clear because it is like element-wise operation. Mean is element-wise. Okay. Now, from this along, we can see that this guy here is our covariance. So essentially, what we are trying to minimize is a trace of our covariance. But we know what the trace of the covariance is. Essentially, it is this is a posteriori covariance. So it is this guy, right? It is I minus LH a priori covariance, I minus LH transpose plus LRL transpose. Okay. All right. And I can open all the brackets here. What I'll find is this expression, this expression. I will skip going over it very fast, in a lot of details. Just, okay, right. I open the brackets, that's what I found. The reason I expanded in this way is I want a quadratic term with respect to L that comes from here and from here. And I want a linear terms with respect to L that come from here multiplied by I and this I multiplied by this. Okay. So basically, I just opened the brackets and I found this those different terms. Now, the rest is quite similar to what we did in LQR. So we find derivative with respect to L and we set it to 0. Here, just present you the final result. You can trust, like, I mean, if you want to take derivative, I showed you the table. So you can follow it to find, how it's done here. So here it is. It is. And now what we can do is like this is the same as this, right? So becomes this guy. I can divide by 2. Can take this to the right hand side. We have this expression here. We can transpose both of them. That's what we have. And finally, from here, the final step is this whole matrix here is full rank because there's a full rank matrix here plus a full rank matrix here, R. I mean, technically, we can imagine it like, no, I mean, it will have to be full rank. It will have to be full rank. So this is full rank, so we can multiply by inverse of this matrix. And that's what we have. That's what we have. So essentially what we found is a formula for Kalman filter gain, which depends on a priori covariance. Now you remember you had a question about why we need covariance. Well, here it is. We need covariances because they describe the process, and optimal gain of the controller will depend on covariances. Essentially, covariances is what we control here. We are not controlling mean because mean stays 0. We are not controlling x because x is random, or there's nothing to control there. What we control is covariances. So our derivatives are taken with respect to covariances. Covariances is our new kind of game, right? We work with covariances, not with variables. That is a key observation for Kalman filter. If covariances shrinks, it means that on average, the process will be stay where we want it to be. If covariances explodes, it means that we become less and less stable. The idea of stability for random processes is a separate topic. We're not going to discuss it. But you can imagine, like just on visceral level, if your covariances increases, it means your process becomes more and more chaotic. If covariances shrinks, it means your errors are smaller and smaller and smaller, right? Yeah. Imagine you have airplane which can go up and down by 1 centimeter. Okay. Now imagine you can shrink it down to half a centimeter. Okay, good. Now imagine on the other hand, it goes from 1 centimeter to 2 centimeters to 5 centimeters to 10 centimeters. Clearly not very good, right? The dynamics here does not indicate anything good for the airplane. If it's going to jump more and more and more, eventually it will just tilt and crash. On the other hand, if it jumps less and less and less, even with a random process applying to it, good. Eventually, it's not going to be like shrinking to infinity because this R and eventually the Q will definitely prevent it from going to zero. You would always have some very randomness in your behavior, but we can at least make sure that it doesn't explode to like it doesn't increase, that your covariance does not increase. Essentially, so you can think of Kalman filter as optimal control for covariances. It is not optimal control for X because X is meaningless because there's a random variable. Like you don't know what it is. You cannot control it. But it controls covariance of X, which is a deterministic variable. So X itself is random. Covariance is deterministic. Mean in our case is zero. Okay. So that is the situation. That is what Kalman filter does for you. Allows you to control covariances. And this is your Kalman filter gain. This is your Kalman filter gain. As you can see, if you are going to actually do Kalman filtering, this is quite easy to code. Like, I mean, it is one line of code. One line of code. In this code, you would have only one problem. How do you compute this guy? Those are the only things that you don't know. How do you compute it? Well, let me show you. You compute it, let me be careful. Okay. So you want a priori, right? You compute it like this. You get your a priori measurement from your previous a posteriori measurement. So this is how you compute it. Quite easy. How do you compute this guy now? Like this guy, we don't know what it is. How do you compute it? Well, from your previous a priori measurement. So you compute it like this. So essentially, Kalman filter, you have two different computations. One is update of your covariances. You compute your a priori, you compute your a posteriori covariance. And you do it on each time step. Update a priori, update a posteriori, update a priori, update a posteriori. And on each time step, you find your optimal Kalman filter gain. Sorry about that. From this expression. That's it. That's it. So if you wanted simply to use it as a recipe, like LQR brackets A, comma B, comma Q, comma R, right? If that's what you want, that's all you need. You just get the recipe from here, here, here. That's and you're done. I think it is meaningful to know how exactly it works, like where does it come from, especially since a lot of our modern tech depends on modifications. So for example, extended Kalman filter is a modification that allows to use this whole thing, but for nonlinear systems. Nonlinear systems. But when you look at the nonlinear systems where extended Kalman filter is used, what you would find is that covariance propagation is, let me just say, not very different from linear systems. Kind of interesting, because covariance propagation is still based on linearization of the dynamics. Yeah. So you can use this understanding to work with extended Kalman filter. Right now, there appears to be quite a lot of interesting work. in observers, in Kalman filters, and so on, which use like more complicated mathematics than this. There is also entire textbook specifically on Kalman filters. So you can, I mean, probably more than one. It's just the one that I read. So it's a big subject, and you can find various corner cases and so on, all of which is not very complicated. So as long as you understand this part of mathematics, I think the rest is quite doable and simple. All right. Now, it is also possible to compute Kalman filter gain like this, which is kind of interesting. You can compute it like this. If you don't like how big this other formula is, you can compute it like this. You use a posteriori covariance times H transpose times R inverse. Looks exactly like LQR. It looks like exactly like LQR gain. Very simple. And the equivalence of those two, I showed in Appendix B. So if you want to see why this is equivalent to the other formula, look at Appendix B. There is a proof. For today, I think we had enough mathematics. So if you're interested, you can look. Here is my proposal, what you can read more on this topic. Quite interesting book. Yeah. Here, if you want, you can look at like a little bit more mathematics on means and so on. Like what happens when the mean is not zero, right? Like you can see the mathematics is a little bit more difficult. And Appendix B is a proof of this property, last property I said, like this one. All right, all right. I hope I did not scare you completely. I know that it is quite common for people to come out of Kalman filter courses with the feeling that there was a ton of mathematics, but the formula at the end was simple. So we can just memorize the formula or look at from Wikipedia and be happy. My personal feeling is completely different. I think the mathematics is quite doable. It is not crazy by any means. And understanding mathematics actually helps you to accept Kalman filter as this like magic recipe for dealing with random systems. If you didn't see mathematics, I don't see how you can accept the fact that it actually optimally controls system with the random noise and random sensor noise and random process noise. So that is just my personal opinion. Right, that is it for today. I'll stop the recording and we can have our questions having.